momentum because I could count the turns that you're going around. So I would have a frequency rate of angular momentum. You see? And that's what they did. Why did they do this way? It actually goes all the way back to a fundamental assumption that was made, that things are spinning in a frictionless environment forever. That is, the assumption is, because if you ask a physicist, what is making the Earth spin? They'll tell you it's because it's in the solar system that's spinning. Then you say, well, what's making the solar system spin? They say, well, it's in the galaxy that's spinning. Well, what's making that spin? Well, that's in the supercluster. Well, what's making that spin? Well, that all started in the Big Bang. You see, son? If it had the Big Bang... Sorry, I'm being cheeky. There was the Big Bang, and then all the energy through everything spinning, and it's been spinning in a frictionless environment since then. So we don't have to account for spin because it's inherent to the Big Bang. First of all, that doesn't tell you where the energy came from to generate that moment of impulse, but certainly it's a very, very large generalization because when you look around, we just happen not to be in a frictionless environment. I mean, it's the same thing at the atomic level. They tell you that electrons spin perpetually because of being in a frictionless environment. They got spinning at the Big Bang, and they're still spinning now at 99.9 something the speed of light, right? Those electrons. Now, that's a lot of spin for a long time. And when you look out there, it just happens that it would be true if there's only one atom in the universe. But as soon as you have two atoms, now you have interacting fields. You have friction, you have collision, you have all sorts of things happening. Gravitational fields acting on each other. Not only that, in order for that statement to be true, then all objects would have to be solid, true and true, homogeneous, which we know they're not. For instance, the layers of the sun rotate at different rates and have huge amount of frictions between them. Think of the inside of the Earth. Is the inside of the Earth spinning in a frictionless environment? I don't think so. It's spinning at a different rate as the surface, obviously because we're getting a magnetic field resulting from a dynamo effect. So what's making the inside dynamo spin against the mantle? You're talking molten lava, not frictionless. Not frictionless at all. Solar winds in our solar system, the gravitational pull of the Earth. You see, here I have two eggs. And don't worry, I'm not going to throw them at you guys. That would be a first. Eh? The presenter throws eggs. Bad crowd. Here I have a hard-boiled egg. Fairly, constant density through and through. Okay? Here, an unboiled egg. High level of viscosity in the middle. Okay? I'm going to spin the hard-boiled egg on the floor. Now imagine this hard-boiled egg was in a frictionless environment, or a very low friction environment. It could spin, whoops, let me try that again. It could spin constantly and homogeneously as it does here and slow down, but that's mostly because of friction on the floor, right? Now let's imagine that it was frictionless, but you could see how that could be possible. But now, let's try to spin an egg that has high viscosity at its core. It stops very quickly. Most of the angular momentum is absorbed by the viscosity of the central core of the egg. Galaxies are just like a non-boiled egg. It has all sorts of density, plasma density change, all sorts of friction, and all sorts of different levels of viscosity. And so is the center of the Earth. There is actually currently no appropriate geological description on how the moment of inertia of our inner core of the Earth occur. How do we get a magnetic field, and what's spinning that dynamo in the center of the Earth? Did you guys have bicycles when you were kids that had those little dynamo on the wheel that created enough current to put up a light in front so you could see at night? Well, in order to spin the dynamo, you still have to pedal. So there's got to be somebody pedaling. There's got to be something forcing things to spin. The new solution that we wrote detached the frame of reference from the rotating metric so that we have an appropriate description of the physics at hand. And the result is that you have torque and Coriolis forces applied to the system directly from the space-time manifold. So let's go back to the analogy of Einstein's field equation of the trampoline curving to generate gravity. So basically Einstein said gravity is the result of space-time curving like the surface of a trampoline. And basically what we say in this paper is that yes, and when space-time curves, it doesn't just curve, but it curls, just like water going down the drain, and that generates spin, angular momentum. And that's the source of the spin of all things. And that is an appropriate way to actually describe physics of angular momentum in the universe. So when we add torque to space-time, the solution gives us a very different picture than a perfect sphere. It generates a torus structure, okay, which is a sphere with two holes in the middle at the North and South Pole. And because it has Coriolis forces are the forces that makes water rotate in one direction in the North Hemisphere and in the other in the South Hemisphere, that makes hurricanes rotate in the opposite direction, that makes plasma dynamics on the sun rotate in the opposite direction. Because Coriolis forces were added to the equation, so what we did is we added a term for torque and the Coriolis forces as a secondary rank tensor on the space-time manifold. The result is a double torus structure, a double torus manifold that has this dynamic, which is viewed here from above as a rotating yin-yang sign, if you'd like. Right. And so that's quite a different picture. And it's quite a different view of the universe, because now space-time is the source for spin, for Coriolis forces, for the magnetic fields, and now we can start to drive the whole equations of creation based on this space-time torque, generating even gravity and electromagnetic radiation. Because you see, now we have a direct balance equation. This is the next paper we're writing right now, is the balance equation that shows that there's a balance between how much space-time torque, how much force is applied on the system, and how much shearing that generates, and how much radiation the system outputs. So now you have a feedback between the gravitational field and the space-time torque. And that was the dynamics that I was looking for. If we look at the torus, from above, what's in the middle? Space, vacuum. The middle of the donut has a hole. This is where singularity would be in the center of a black hole. So at the center of the space-time manifold, where we would expect the